Hi everyone. So we have been discussing the mathematical modeling of the infectious diseases, and now we're going to cover the empirical side. The aim is to see how these models are fitted or used in practice. As we shall see, estimation is a lot easier when we understand the maths, though there are considerable data related challenges which the practitioners address through a combination of art and science. So art and science is what we're gonna see. We shall cover a sample of the models that have been applied in the UK, and you can replicate the models for other countries. We are going to split the coverage, so in this video we are going to focus on one of the key parameters, the contact rate, which we have seen plays an important role in the transmission of the disease and is a key parameter in the mathematical models that we have discussed. For example, in the simple SIR model, where the population is assumed to be homogeneous, we had the three compartments. We have the susceptible population. Anyone who gets infected flows into the infective compartment, and the ones who recover then flow into the recovered compartment. We represented the rate of flows with the two parameters, beta and gamma. In the deterministic case, we model the dynamics of this compartmental structure in terms of the differential equations. So the susceptible population declines as the individuals get infected. The rate of change of the infective compartment is then just the inflows from the susceptibles minus the outflows to the recovered. So the size of this compartment grows as people get infected but declines as people recover. The estimation of this beta is the parameter of interest in this video. We know is the per capita rate at which individuals have effective contact per unit time. You know what's meant by effective contact, right? It really depends on the disease and really means that if an infected were to have this type of contact with the susceptible, then the susceptible is going to end up in the infective compartment. You can see it will depend on the infectivity of the infective, the susceptibility of the susceptible, length of the contact, and the hygiene that they practice. But to simplify, one can just say that this is just the product of the contact rate and the transmission probability given the contact. So if we can establish a proxy for the contact rate, then we are one step closer to the estimation of the beta. Now this SIR model is a good start, but you can see it assumes every individual is the same. And as we know in relation to the COVID-19, there's a lot of interest in how the disease is affecting different regions and people of different age groups. So one needs to account for the heterogeneity. But worry not, we can segment the population into different groups and then have a variant of SIR. We can have as many subgroups as we like, but just for illustration, let's say we have two groups, so we will now have 6 equations, 3 sets of 2 equations. We saw this situation in the previous video. We will just write the infectives. So group 1 could be younger and group 2 could be older. Now we have 4 betas, but the main thing is we still have beta, so things don't change much. We just have more parameters to estimate. Now let's say in the simple homogeneous case, we know that the number of infectives will be some function of the initial conditions and the model parameters. For example, in the SI case, we had an explicit solution. So one can say that if we know the number of infectives over time, we can try to determine the parameters by fitting the equation to the observed data. Surely this would be slightly more involved process in the heterogeneous case, but still doable. However, this approach is not commonly used in practice, especially in the initial stages. Potential reasons being the data on the number of cases is usually not reliable, and the individual parameters are usually easier to estimate. For example, one can estimate the infectious period using a sample of observed cases. So the approach commonly adopted is to estimate the parameters individually. One can then validate the overall output against the actual data allowing for uncertainty expected based on knowledge of the administrative processes. We know it can include things like the number of tests performed, etc. As you would have seen, one of the first estimates that becomes available is R0, and we know from the first video that R0 in the simple case is related to the parameters as follows. This is just the basic reproduction number, by the way. So one can easily estimate beta using this relationship, but for the more complicated cases, the relationship might not be so obvious, so let's consider some alternative approaches that one can use to estimate the contact rate. This is a key component of the transmission process. The easiest place to start is to see how can one go about estimating the contact rate or interaction between different countries. For the UK, for example, one can look at the international travel data. So the more people who travel to or from an international country, the higher the interaction or contact rate with that country should be. Usually, this is estimated using surveys, so the international travel data can be used as a proxy for the contact rate between the countries. But here, we are after the contact rate within the country, so we need more granularity. For the domestic case, several such proxy type approaches have been used. For example, a survey of a random sample of population can be used to estimate how many people does a person interact with, and one can then also explore whether the contact rate varies by, say, age, region, distance, etc. So this requires a very large sample, which comes with the considerable logistical challenges, so one has to keep it simple. This survey-based approach is the focus of this video. Many researchers have also used structure-based data. For example, we know individuals live in a household. This is where they should be spending most of their time. And then depending on the age, they will be going to workplaces or schools and different types of communal places. The data on the characteristic of the households and workplaces and school is available through the census. So one can use such data to create a model of the structure of the society. One can then complement this data with mobility and travel data to create a model of how people interact. The census data is available at the output area level, so this allows for more granular modeling. One can increase the granularity further by making use of satellite images and other geographical data this available at more granular level. Essentially, you take the census data for a local area and distribute it over the area based on, say, the type of buildings or night lights you see in satellite images, and one gets very close to a network model. We shall cover two examples of such structure type models in the next video. These are the so-called meta population model and the individual based model. Let's start with the social context surveys. A similar study in this space is the so-called POLYMOD study. It was a European public health project, and the paper is freely available here, so please have a read. Essentially, they conducted a survey of participants across 8 European countries to estimate the contact rates and patterns. The aims of the project were quite ambitious. However, the study is mainly known for the contact matrices among different age groups. You can find other studies that have extended the finding to other countries. For example, here is one study that has projected the matrices to 152 countries. Let's see summary of our study. So we have the names of the 8 countries, the number of participants in each country. So on average, they surveyed around 900 people in each country. These participants reported how many people they had contact with over one day. The contact was defined as face-to-face conversation with more than 3 words, or physical contact such as handshake, kiss, etc. The last column shows the average number of contacts. So in Britain, for example, an average person has conversational or physical contact with about 12 people. In terms of the survey, what they did is to pick a day in advance and then fill in a questionnaire like this for the chosen day. So you would have to fill in a row for each person you had contact with on the day. In the first column, you give the age of the person. You can give the age range if you don't know the exact age. You then tick the gender and then whether the contact was physical, and the other columns then just capture more contextual information such as how often do you meet this person, where did the contact take place. This is the information about the people they contacted. The survey also collected information about the participants such as their age, gender, location, etc. The aim was to see if the contact rates and patterns differ by these variables. You can see the data provides quite detailed information that one can use to infer a lot of information about the contact patterns. However, as we saw, there are only about 900 participants in each country, so a more granular analysis is going to be problematic. So we just focus on the main findings. This is the contact rates by age. Let's say we divide the participants into age groups, say younger than 10, 10 to 20, and so on. Let's represent the number of participants in group 1 by P1, the next age group by P2, and so on. Let's apply the same grouping to their reported contacts. Let's C11 represent the number of people of age group 1 that the participant in age group 1 reported to have contact with. C21 then represents the number of people in age group 2 that participants in age group 1 had contact with, and so on. For the participants in the second age group, we can similarly write. So the second index has become 2 to indicate that these are the contacts of the people in the second age group, and similarly for the other age groups. We saw the study covered 8 countries, but we are going to focus on the UK, as the number of participants was only about 1,000 and they reported around a dozen contacts on average. One won't necessarily have data in each cell, and the more granular the age groups, the more sparse this matrix would be. So one will need to use some form of interpolation or smoothing. The problem is very similar to what we had when we were calibrating the local volatility model. Remember, we said this is one of those problems that the mathematician called ill-posed. One encounters such problems in many fields, say restoration of a blurred image, or the images from one of those night outs. The various alternative methods that we discussed there apply here. For example, one can use thin plate spline interpolation. It's similar to spline interpolation but two-dimensional. So it is like fitting a thin metal sheet through the known data points. We then also discussed that the known data points may also have measurement errors. So interpolation will probably produce rough surfaces. And we then said a better way would be to use some smoothing methods, say regularization or regression-based methods. One can use the same methods here, so we are not going to repeat the details, but let's mention that here the most commonly used method is Contagion, which really amounts to Gaussian regression and comes in both interpolation and smoothing forms. So if one insists that the data points have no measurement error and want the fitting function to go through all of the input points exactly, then Contagion interpolation is the method. Otherwise, the smoothing method is used, which produces smoother function. And when it comes to regression, since the number of contacts is a discrete variable, one can use Poisson regression, but then Poisson has only one parameter and amounts to assuming that counts are independent. So negative binomial regression, which is like a more generalized version of Poisson, is commonly used. Names sound complicated, but they are not much different from the familiar regression. One just replaces the probability distribution. So in normal regression, we assume Gaussian distribution, and Poisson regression, we have Poisson distribution, and the negative binomial, it is Poisson gamma mixture. So you get an additional parameter, and you're no longer forced to have the mean equal to variance, which pleases a lot of people. So negative binomial is the regression to aim for. And summary then, the interpolation and smoothing can be used to fill the missing values and or get more granular contact matrices. One also needs to correct for inconsistency in the survey data and transform it into a useful form. So let's explain these adjustments by focusing on a 2 by 2 matrix. Now the first column represents the number of contacts that participants in the first age group had with people in the same age group and with people in the other age group. So if we divide by the total number of participants of this age group, which is P1, we get the average number of contacts. This is useful because we will need to apply this matrix to the total population of the UK. So the average provides us a way to translate the results based on the survey sample to the total population. We can do the same for the second column. We can represent the average by M. So M11 represents the number of people in the age group 1 that an average person in age group 1 had contact with. M21 represents the number of people in the second age group that a person in the age group 1 contacts, and same goes for the second column. Now we can apply these averages to the total population, so let's represent the total number of people in age group 1 by N1 and the total number of people in age group 2 by N2. Multiplying the average number of contacts by the total number of people will give us the total number of contacts. Now for consistency, the off-diagonal entries must be equal because the number of contacts that people in age group 1 make with people in age group 2 must be equal to the number of contacts that people in age group 2 make with people in age group 1. But the survey results might not obey this equality because it is estimated based on a sample. It's easy to explain with some figures, so let's say the average number of contacts matrix is as follows. So a person in age group 1 on average has contacts with 5 people of the same age group and with 2 people of the second age group. Now assume that in the total population there are 100 people in the age group 1 and 20 people in age group 2. We can now calculate the total number of contacts that the population make. So multiplying 100 by 5 gives the total number of contacts that people in age group 1 make with each other. Multiplying 100 by 2 gives the total number of contacts that people in age group 1 make with people in age group 2, and same goes for the next column. Now clearly this matrix is not consistent because people in age group 1 are claiming to have 200 contacts with people in age group 2, but people in age group 2 only recall having 20 contacts with people in age group 1. So to fix this inconsistency, we just have to make the matrix symmetric. There's several ways to do this in algebra, but the one based on average seems more appropriate. In general, this amounts to taking transpose of the matrix, which means keep the diagonal elements as they are and swap the positions of the other entries. So if we represent the original matrix by A, then this is just the transpose of A. Now we can calculate the element by element average of the two matrices. The diagonal entries are easy. For the non-diagonal, we just sum the entries and divide by 2. So we sum these two and divide by 2 and then do the same for the other entry. And you see the matrix has become symmetric. So essentially, we sum the matrix and its transpose and divided the resulting sum by 2. We can now translate this matrix back into the average form. We know the total population of the two age groups. So if we divide 500 by 100, we get 5, same number as before. And if we divide 110 by 100, we get 1.1. And same calculation for the second column gives. So you can see 2 has gone down to 1.1 and 1 has increased to 5.5. But now if you use these averages to calculate the total number of contacts, you would see they're consistent. For our symbolic matrix, what it means is we just replace the off-diagonal entries by their average and the diagonal entries stay as they are. And you can divide the entries in each column by the respective n to get the average matrix. So this is the kind of adjustments that you will see applied in many papers to make the matrix consistent. In summary then, one has to use smoothing or interpolation to fill the missing values or to get more granular results, and one has to make adjustment to the matrix so that it has the reciprocal property of contacts. Now we can go back to the findings of the paper. For the UK population, they came up with this matrix. I have highlighted the diagonal entry so that we can see the pattern. If you sum across the rows, you get the contact rate by age, the pattern in which is easy to see when one plots the result. So younger people are making more contacts. To see other patterns, first let's delete all entries below 0.5. So you see more contacts along the diagonal, meaning people prefer meeting people of their own age group. This is called associative mixing. Essentially, people mix with people who share the same characteristics. To see the patterns more clearly, let's remove all entries below 0.9. So you can see the diagonal stays. The other dominant entries could be down to parent children. People in their 30s would have younger children, say younger than 10, whereas people in their 40s would have teenagers. Now, this study was performed like 15 years ago, and we know a lot has changed since then. Virtual world is taken over, so one expects the social contact matrix would have changed. Luckily, BBC recently did a similar study using a mobile app. This was a citizen science project for a BBC documentary, which is available on YouTube, so please do watch the documentary when you get a chance. They conducted two sets of surveys, one focusing on a small town and the other based on UK-wide samples. So we will just discuss the UK-wide results. The way it works is a volunteer downloads an app. The user then enters the demographic information. The app will record users' hourly location to the nearest square kilometer to allow for analysis of people's mobility. The user will then enter the contacts directly, so the count of contacts is still based on self-reporting. The structure is very similar to the previous study we discussed. So the first part is the same as the user filling the demographic section we saw, and the last part is the user filling the contact report. The key innovation is the user mobile app, and the main improvement is the sample size. BBC managed to get 40k respondents, which is 40 times larger than the POLYMOD study. And these participants reported around 400k contacts. An advantage of the larger sample is we can be more confident when splitting the matrix, say by contacts made at home, work, or by other characteristics such as conversational versus physical, or weekday versus weekend. The survey and results have been documented in this paper. It is freely available, and there's also an earlier version of the paper by the same guys which contains a bit more details on the methodology that they used. You can also download the matrices from the supplementary material section. They have uploaded both the raw matrices and the adjusted matrices, which they call the reciprocal matrices, so you can have a look at how the adjustments are made. The BBC matrices are slightly different from the POLYMOD, most notably in the contacts rate of the younger people and the split of the contacts between the physical and conversational. You expect fewer physical contacts between the people living in the virtual world, so no surprise, but the overall results are broadly similar. The other differences that you see were primarily because of the sampling differences between the two. For example, BBC didn't have younger people in the survey, whereas the other survey sampled the younger people, so there are some differences there. So in symbols then, the social contact matrix takes the same form. This is the adjusted matrix, so we represent the m's with tilde. Now this matrix gives the contact rate. If we multiply it by the transmission probability, we get the next generation matrix. Notice there is implicit scaling happening there as well, because the contacts are counted over 1 day, but the infectivity will last longer than 1 day. So the Q we see here captures a lot of things: infectivity, susceptibility, and the scaling of the contact rates, which are estimated using a proxy definition we saw. Remember, conversation of more than 3 words or physical contact. A different definition of contact will give different contact rates, though hopefully the pattern won't differ much. So the Q isn't really a probability, it's more like a scaling factor. The Q can be calibrated using the basic reproduction number or the actual infectious data. Here we are assuming the same Q applies to all groups, but we can have it vary by group so we get better fit. Now you can calculate the eigenvalue and eigenvector of this next generation matrix to get the R0 and the stable distribution of the infectives. Remember, these refer to the dominant eigenvalue and the eigenvector associated with the dominant eigenvalue. We covered these in detail in the R0 video, so I'm not going to repeat the details. And one can also transform this into the beta of the SIR framework. So one has to divide by the number of susceptibles so as to get the per capita rate, and then by the length of the interval to get per unit time rate, which is what beta is, right? Now the contact matrix we saw shows that younger people make more contacts and there is preferential mixing by age. So we should be expecting more young people to get infected. But when you look at the COVID-19 data, you see a lot more older people. This chart is from the UK surveillance report, by the way. It's not due to the population mix, as the population mix by age group shows we do have a lot of young people as well. So what gives? Could it be because the infectivity and susceptibility vary by age? Or could it be the severity of the disease differ by age and we are only testing people who are showing the more severe symptoms? Anyways, I'm gonna leave it to you guys. Now the contact matrices that we saw has age as the key differentiator, but we know there are a host of other factors that are important, say risk behavior. For example, some people by the nature of their jobs meet more people. For example, people working in shops, delivery, or schools meet a lot more people, so their contact rate should be much higher. Similarly, people living in dense cities or bigger households would have higher contact rate, so one should factor these factors in. Easier said than done though, because data collection is hard. We shall consider the impact of households, workplaces, and region in the next video when we consider the meta population and individual based models. There are also a few more subtle issues with this type of survey-based approaches. It doesn't account for the fact that people may change their behavior when they're ill. So a person who goes to gym may be heading to pharmacy instead when ill, or just staying at home. These studies being conducted in peace times will not reflect what happens in the pandemic situation. Also, the contact rates and pattern change over time and definitely over the course of the pandemic. So one has to keep repeating the survey or find some other mechanism for ongoing calibration of the contact matrices. Now the next logical step would be to use a mobile phone location data. One can also automate the contact reporting by counting people in the immediate vicinity of the individuals. These have to meet the privacy requirements though, so the data sources exist but one can't use them. Some apps are being tried. Please look up the NHS contact tracing app, but these have to be less than ideal as one just can't use all the data without consent. A bespoke network is also possible, so you give people devices and these devices speak to each other, so one can automatically determine who has come into contact with whom, and one can also filter by the length of the contact, etc. So this will provide for more accurate estimate of the contact rates and patterns, and also identify the people who are making more contacts than others, so one can have meaningful segmentation. So a lot more is possible, and watch this space, right? So hope you enjoyed the video and I look forward to seeing you in the next.